Now we'll enter sections 6.5 and 6.6 as the last, I think this is the last section that we'll have here for chapter 6. So as we go through, there will be elements that will be some review questions, some will be new content. As always, jump in, interject, shout out if you have questions as we're going. You don't have to wait. If you have something that you need a question on, just answer it right away. As I've been in my quiet time and prayer time these last few weeks, actually it's even longer than that, this concept of being interruptible, that you get in this rhythm and this pace, which I like to do. I like to have a pace and a rhythm and a routine, but when I don't give myself time to be interrupted, I miss out on opportunities to talk and pray with other people, or even for the Holy Spirit just to work in me in those moments. And so in that same vein, interrupt when you need to interrupt, so we can get all questions addressed. So here you go. Take a moment. See how you would, if you could take this and set it up into an equation. So that's the first goal is, can you take this and try to set it up into an equation of some kind? And the reason why I know it's an equation, it has the word is equivalent, all right? So is equivalent to, as soon as there's an equal sign, I know there's an equation. So take a moment, see if you can write that down and how you would write that as from this word model into an algebraic model. So it starts with if a certain number. As you read that and you read if a certain number, what is that going to create as a memory or an idea or a concept for you? A certain number. Any number. So n, or possibly x. If it's unknown, we have something that's unknown. All right. So if you were stuck on where to get started with something like that, say, all right, now we got this unknown. What do we do with that unknown?
Minus 919.
Say that again.
Minus it from 919.
All right. So tell me how you would do that.
Put a subtract sign.
Where?
So I write x minus 919 is equal to
X minus 919.
is equal to.
All right. It says this number is subtracted from the numerator and added to the denominator. Is that what we have going on here? No.
9 minus x over 19 plus x.
So 9 minus x, I hear. Subtracted from. When you're subtracted from, that means it'll be 9 minus whatever that is. If 9 is, it's, what is subtracted from which one? So this numerator is 9 minus x. So some number is subtracted from 9. And then denominator, 19 plus x. So again, as we're going through this, it's then remembering, okay, what is the numerator? What is the denominator? So it's getting back at some of our vocab words. All right. Is, to the denominator of 19. The new fraction, so now this is my new fraction. 9/19 was the old fraction. This new fraction is equivalent to 1/3. Biggest challenge in these scenarios typically is how do I start by getting it set up? So set something up literally go back through. After you set it up, if you're unsure, after you set it up, go back through and reread what the problem says and see if that matches identically. If not, try again. So that whatever number is subtracted from the numerator, and the numerator was 9 minus x, 19 plus x. And then it's a matter of saying, okay, well, now what do I do? How do I solve? Different aspects, different ways you could go. How would you start?
I blanked on how to start, but x equals 2.
All right, so you...
I just knew that 7/21 is 1/3, and that 2 gets there.
7/21 is 1/3, so you found that x is 2. Yep. And seeing that is a possibility, but then you got to work back, especially if I say in the question, solve it algebraically, which I usually do because I want you to use some algebra. So on the upside, you'll know if you know that it's 7/21. Well, if I work through this problem and I get the wrong thing, I at least know I did the answer right. I got to go back and look at my work. So it gets to that idea of why I assign check your understanding odd problems. So that way when you look in the back of the book, you got the answer there. And if you didn't get the answer, you knew you did something wrong in the process. So we've been doing fractions so far. What do we typically do when we have fractions? Well, before we can reduce, we're usually looking to find a common denominator. All right. So when we look at the left side, my denominator is 19 plus x. On the right side, my denominator is 3. So my common denominator will be 3 times 19 plus x. How do I get this to have a denominator of 3 times 19 plus x? I will multiply it by 1. On the left-hand side, I need to multiply it by 1. Because when we multiply by 1, I don't change the value. Anything times 1 is itself. So this times 1 is still just itself. This 1/3 times 1 is still 1/3. But now I will have common denominators. On the left, I will have 3 times 9 minus x over 3, 19 plus x equals 1 times 19 plus x. I didn't write the 1 times. You can if you want to. Over 3 times 19 plus x. When I have them equal to each other, if this whole thing equals this whole thing and they both have the same denominator, that means I'm dividing by the same thing. It'd be like up here saying, well, I have 7 over 21 is equal to what over 21? Well, it'd be 7, because it's the same thing. When the denominators are the same with equal fractions, the numerators have to be the same, which means these have to be equal to one another. Those are equal. Three times 9 minus x is equal to 19 plus x. I just took that numerator and rewrote it. At which point you should be able to look at this and say, algebra. We've done this a bunch of times. I can jump in, do distributive property. 27 minus 3x equals 19 plus x. If I subtract 27 from both sides and subtract an x from both sides, I will have negative 4x equals negative 8. Divide by negative 4, x equals 2. And then go back and reread the question. It says find that number, which I did, which is good. Sometimes it's a matter of like, they're going to ask you, or I might ask you something to do with that number. So you just got to go back, and when you solve it, make sure you actually answered the question then as well. A certain number, find that number. X is 2. Take a moment, solve those 3. First one here, same denominators. X must be 3. When the denominators are the same, the numerators have to be the same if they're equal fractions. All right, now if we jog back our memories a little bit, you possibly learned this phrase in somewhere in your mathematics history. Maybe you've heard the words cross multiply. So when I have equal fractions, I could multiply across 2 times x is 2x. 2 times 3 is 6. And then x equals 3 when you divide both sides by 2. This is actually what we did on that last slide. We found the common denominator by multiplying and then set them equal to each other. And you ended up multiplying each, the denominators of each times the numerators of the other side. Using that same idea, or if we take what we did on the last slide, if I do it here, multiply this by 6 over 6, multiply this side by 3 over 3, I get a common denominator of 18. I wouldn't have to do that large of a number, though. I could multiply just the left side. Ooh. Come on, erase. Oh, that's why. I have it on my pen. If I multiply the left side by 2 over 2, then I'll have 2x over 6 equaling 5 over 6. Since they are the same denominator, the numerators must be equal. X equals 5 halves. If I do that cross multiply concept, 6 times x equals 3 times 5, divide by 6, x equals 15/6, which is the same as 5 halves. What's my final answer on the third one here? X equals 21/5. Use that same idea here. You tell me what to do.
Cross multiply.
Cross multiply. Tell me what you're going to get when you cross multiply.
You get 7x minus 14.
7x minus 14. That would be this 7 times that. And yep.
Over 7.
Equals 35. Yeah. So when we cross multiply, we're getting rid of the fractions. That's the goal. Again, most people don't like fractions, so we come up with methods and procedures to work not in fractions. All right. Then what? Carry on.
Add 14, get 49, x equals 7.
7x equals 49. When you add 14, x equals 7. Did anybody do it a different way?
I just set them equal to each other because the denominators are the same.
The denominators are the same, which means the numerators must be the same. X minus 2 equals 5. Add 2, x equals 7. So much like when we talked about solving quadratics, when you find a method that works for you and you just want to stick with it, that's fine, you can stick with it. Sometimes there might be shortcuts, so to speak. But if you don't want to worry about that and you say, this works for me, I understand this, I'm going to go with it, then use that method. Then we look at this and say, all right, which method do we prefer? Because if we go with cross multiply, I'm going to have x plus 6 times x minus 2. And I'll have 2 times x plus 2 times x minus 2. If I notice that the denominators are the same, I will have x plus 6 equaling 2 times x plus 2. In the yellow up here, I would have to do FOIL before I could solve this problem. And on the right side, I'd have 2 times x squared minus 4. And then keep working through that problem using the quadratic formula. Setting them equal, because the denominators are the same. Distributive property. Subtract an x from both sides, subtract 4 from both sides. X equals 2. And I'm not circling it because I'm going to go back up here and remember when we had this conversation. Domain. Looking at that original equation, which if I get rid of this here, looking at this original equation, are there any restrictions on what x can be?
Yeah, x can be any real number that is not 2.
X can be any real number that is not 2. If I put 2 in here for x, I have 2 minus 2, which is 0. Can never have 0 in the denominator. If I put 0 or 2 in here. So although when I solve this equation, I get x equals 2, it makes the numerator work. However, the denominator is undefined then. So while this is a solution to the numerator, when I set it up, it does not work back in the original equation. So this would be what's called an extraneous solution. Extraneous. Extra but doesn't work, extraneous. So it's a solution, but when I actually put it back in, I get an undefined answer. So I started with some of these with same denominators. Now we look to them when they have different denominators. And in this case, because now I have 2 terms on the left, I can't just use cross multiply anymore. Cross multiply only works if I have a single fraction on the left and a single fraction on the right. Now I can do that, or, as I prefer to do, we are going to clear the denominators. And the way we clear the denominator is multiplying everything by by the lowest common denominator. So in this case, my denominators are 2x minus 1 and x. So my lowest common denominator is x times 2x minus 1. And I'm going to multiply everything by x times 2x minus 1. When I do that, this first fraction will be 2x in the numerator times x times 2x minus 1 all over 2x minus 1. My next fraction will be 1 times this, which is, 1 times x times 2x minus 1 all over x, then equals. Third thing is, again, 1 times x times 2x minus 1 all over 2x minus 1. So again, what I'm doing each time, this, if you want to think about it, is a fraction. It's x times 2x minus 1 over 1. So it's this times the first fraction, this times the second fraction, this times the third fraction. I'm going to write it all out so I see it all together. Do that before I do any type of reducing. If you try to do reducing too early, I see this so many times. You forget something somewhere thinking you did it for one fraction but not for the other fraction. So each fraction operates independently. They're all different terms. So clear the denominator. Multiply by the lowest common denominator. So when I say clear the denominator, that's what I'm doing. I am multiplying everything by the lowest common denominator. So once I figure out the common denominator, I just multiply everything by it. What happens here? Well, I recognize that 2x minus 1 in the denominator, although not typically written, is in parentheses. Instead is identical to the 2x minus 1 in the numerator. They reduce to 1. 2x minus 1 over 2x minus 1 is 1. Leaving me with 2x times x. Next fraction.
2x minus 1.
The x and the x reduce. X over x is 1. So it'd be plus 2x minus 1. On the right side, well, the 2x minus 1s again are identical. They divide to 1, leaving me with x. 2x times x is 2x squared plus 2x minus 1 equals x. I have a quadratic. To solve quadratics, first thing I have to do is set my quadratic equal to 0, which means I need to move this x to the other side. I'll have 2x squared plus x minus 1 equals 0. And then I can do completing the square, quadratic formula, factoring, or if I recognize that it's a special form, I can do that too. For this one, when my first number is not a 1, I tend to not do factor just by looking at it and doing the X box. I usually go either to the quadratic formula or I personally go to completing the square. It does not matter to me which one we do. If it's the quadratic formula, recall that that's the quadratic formula. If you don't memorize that, you don't have to. This is like I did for the first exam. You can have a sheet of paper, formulas on it, definitions on it, example problems on it. So here, negative b is the middle term. Middle term here is a positive 1. It will be negative 1 plus or minus the square root of b squared is 1 squared, so that's 1, minus 4 times a times c, all over 2 times a. And the a, b, and c are the numbers in front of the coefficients, a, b, c. X equals -1 plus or minus the square root of 4 plus 8. 4, that's not a 4. 1 plus 8 all over 4. X equals -1 plus or minus the square root of 9 all over 4. So this would be -1 plus or minus 3 all over 4. -1 plus 3 over 4. X equals -1 minus 3 over 4. Those are my two answers. Go back to my original equation and remember, oh, I have fractions up here. So I need to be considering domain restrictions. X cannot be 0 is definitely one of them. How do I know that? Well, right there. That X cannot be 0 because 1 over 0 is undefined. And then also I have this, 2x minus 1. It also cannot be 0. So if I'll take this over here, 2x minus 1 cannot be 0. Add 1 to both sides. 2x cannot be equal to 1. Divide by 2, x cannot be 1/2. That is an extraneous solution. So as an entire question, if this is an entire question on an exam, you get everything except you forget this. If I asked you to talk about domain and you identified that it can't be 1/2 and still said it was 1/2, it's going to be a 3 out of a 4, which is mostly correct, which is B. That's B work. All right. If I do not discuss domain and you come up and just say there's these two solutions, you're probably going to get a 4 because it's essentially correct. If I do not say to discuss domain, you identify these two solutions and say that this is extraneous, those are the conditions when I say that's extra points. That's going above and beyond what I was expecting in a problem. So that'd be like either a 4.5 out of 4 or a 5 out of 4. Where it offsets maybe other areas where you maybe lost some points or didn't earn full credit, I should say. You're not losing them, you just didn't get fully there. All right, and then these are the famous ones that people put out there. Train leaves the station. I mean, it's not quite the same way. In a case like this, though, before I get started, we're going to say distance equals rate times time. Not an equation I'm going to expect you to remember. It would be something on a test question that I would include somewhere so that you remembered what it was. So distance equals rate times time. So we have a plane that flies with the wind, 465 miles with the wind and 345 miles against the wind in the same length of time. So between the two, the time is the same. So I've got one scenario, distance equals rate times time. So the distance is 465 miles. The rate we don't yet know, but we know that the time is the same. So I'm going to just use time the same way. So in looking at that, the speed of the plane is not identified yet because it says later we're going to find the speed of the plane in still air. So here, when it flies with the wind, that means the rate of the plane is being enhanced by the wind. And the speed of the wind is 20 miles per hour. Because in the question it says, if the speed of the wind is 20 miles per hour, there's that. I've got a second equation, which will be distance equals rate times time. But now the distance is different. It's now 345. And my rate is against the wind or into the wind, or my speed minus 20. Some of you may question, is this actually how it works? Yes. If you've ever flown on a plane, and here's the expected time it takes you from liftoff to touchdown, and then when you actually get on the plane, like, oh, we're going to get down a half hour early. Why? Tailwind. All right? And you typically get prevailing winds that go west to east across the U.S. So on the way home, it usually takes you longer if you're coming back to California from the east than it takes to get there. I just returned from D.C. It took us 4 hours and 5 minutes to get there and 5 hours to get back. An extra hour of flight time because we're coming into the wind. And it says they did all of this in the same amount of time, not equals time, times time. It's rate times time. This time and this time are the same value. They're the same number because it says they want these different lengths in the same length of time. What does it mean when the same length of time? It means that the time from the one is equal to the time of the other. So to solve this problem, I'm going to divide both, in this side, divide by that. So I'll have t equals 465 over r plus 20. Over here, where's my equal sign? I didn't draw it in there. Apologize on that. The equal sign is right here. 345 equals. Divide both sides by r minus 20. So I will have t equals 345. 345 over r minus 20. And up here they said they had the same length of time, which means this time is the same as that time, which means 465 over r plus 20 is equal to 345 over r minus 20. Also for reference, moving forward, on the exams, now when we have our second exam and eventually the final exam, the problems that you're assigned, I will also typically tell you what chapter it was from. So that way if you're going, I don't know where to start. Oh, but this is from chapter 6, because it'll say from chapter 6, and then here's a question related to chapter 6. If you have that page of notes and you have some things from chapter 6, you can at least remember, oh, these are the type of problems we did. I'm probably going to need to set it up as either a fraction or like we did in the last couple sections, doing quadratics or synthetic division or quadratic formula or something along those lines when we're talking about rational expressions. But now we've got two fractions that are equal. We can either clear the denominators or we can cross multiply. What do you want to do?
Clear the denominators.
If we clear the denominators, I'm going to multiply by my common denominator. My common denominator is going to have to include this value and that value, which means I'm multiplying everything by r plus 20, r minus 20. So when I do that, I will have 465 times r plus 20 times r minus 20 all over r plus 20 equals 345 times r plus 20 times r minus 20. And this side is all over r minus 20. These reduce. Those reduce because they're identical. On the left, I have 465 times r minus 20 equals 345 times r plus 20. At that point, it's not a quadratic. I have r as my only variable. I have a couple parentheses. Your instinct, I would hope, is distributive property. 465 times r, 465 times negative 20, be a large number, equals 345 times r plus 345 times 20. Move your r's to the left, move your numbers to the right, divide and come up with the rate. When you do, though, you have to go back and say, what was I looking for? Find the speed of the plane in still air. In this scenario, speed plus 20, because it's 20-mile tailwind, speed minus 20, that was with a headwind. So when I do find r, r does answer the question of the speed of that plane, the rate of that plane in air that is still. So again, when you get to the final answer, like, oh, r is this, go back to the question. What was the question actually asking for? Was it asking for a rate? Or was it asking for what's the speed of the plane with a tailwind? Well, if that's the case, then you do that number plus 20. What was the speed of the plane that had a headwind? Then you go that number minus 20. In this case, it just says the speed of the plane in still air. The r that we get is the actual value that you would have for this problem. A little quick review. I shouldn't say quick. A little review. Solving for equations. Can be done a couple different ways. We've done matrices the last couple times, so this time I'm going to do probably substitution and linear combinations. What I'm going to do first is I'm going to notice that this equation and this equation both have just a single z. So I'm going to solve this equation for z, and I'm going to solve this equation for z, and then set them equal to each other. So in this case, I'm going to add z to both sides. And I'm going to subtract 5 from both sides. So when that happens, I'll have x plus 2y minus 5 equals z. Here I'm going to add z to both sides and subtract 1 from both sides. So I'll have 2x minus y minus 1 equals z. And since those two are equal to each other, well, they're both equal to z. And if they both equal z, then they equal one another. X plus 2y minus 5 is equal to 2x minus y minus 1. And as is the case in all these three equations, I have all the variables on the left and all the numbers on the right. So I'm going to take this and move all my variables to one side. Subtract 2x and add y and add 5. Subtract 2x, add a y. So if you notice in the equal sign, those are the same values. Subtracting 2x, adding a y, adding a 5 to both sides of the equation will give me negative x plus 3y plus 0 equals 4. And then say, all right, well, what else can I do? I can take these two equations since I see that one has a negative x and the other has a positive x. I could do a similar thing. Or take these two, and this is what I'm actually going to do, and I'm going to do it for z. Since I already have this one solved for z, I'm going to solve this one for z. To solve it for z, I'm going to move the z over to that side and the 11 over to this side. And I'll have negative x plus 3y minus 11 equals 2z. Divide everything by 2. Negative x over 2 plus 3 over 2y minus 11 over 2 equals z.
Wouldn't it be negative 2x?
Negative 2z?
Oh, yes.
Yes, negative 2z. Sorry about that. Which makes, yep, this is a positive. Gotta change my signs there. This will be negative. This will now be positive. So when I move that 2z over, it's negative 2z, yes. Then divide by negative 2. Now it's positive 11 halves, negative 3 halves, and positive x over 2. These are equal to one another. So I will set them equal to each other. 2x minus y minus 1 equals the one I just did there, x over 2 minus 3 halves y plus 11 halves. Move all my x's and y's to the left, so minus x over 2 plus 3 halves y. And this 1 has to go to the other side, so I'll add 1 to that side. Over here, minus x halves plus 3 halves y. Two minus half of an x is 1.5 x, or 3 halves x. Negative 1 plus 1.5 is just a half, so I'll have y over 2 equals 13 halves. Remember the work we just did on fractions? They all have the same denominator. Since they have all the same denominator, I can only look at the numerators and rewrite my equation like that. Now I've got these two equations to work with that only have x's and y's, and that's what my goal was. Can I combine two different sets? So the first set that we combined were these two. Right here to get me to an x and y equation. And then I use these two to get me to an x and a y equation. And now I just have x's and y's. I'm going to just take this one and write it underneath that one. Or that's how we would normally have it set up in the first place, and say, all right, well, how do I use combinations to eliminate a variable? I'm going to take this equation and multiply it by 3. If I multiply this whole equation by 3, I'll have 3x plus y equaling 13. I'll have negative 3x plus 9y equaling 12. Add those equations. 10y equals 25. Y equals 25 over 10, which is 5 halves. Take this. Sorry, that's not a very good circle. Take that y equals 5 halves, put it back into one of these other equations. I'm going to probably put it right there into this equation. 3x plus 5 halves equals 13. Subtract 5 halves, divide by 3. Then take whatever that x value is that we solve for here, this y value we solve for there, and pick one of these equations with z to substitute back in. So in this case, a little substitution, little linear combinations, get to an x, y, and a z. Again, I typically in a question like this would go to matrices, because I find that matrices help keep me organized more, because I know that's one of my own flaws. And as you've already pointed out, I also lose track of negatives. So really watching and managing those as well. But as I'm grading your papers, I'm doing that, and I'm looking at saying, oh, they missed a negative somewhere along the lines. Did that change? Did they, aside from that, do the entire process correctly? If the answer is yes, it's a full credit 4. Take a moment and solve that using all the ways you know how. And by that means, if you, so one of the ways we've already done it today is a quadratic. We can do factoring, which would include likely the Xbox method if you want to go that route. And then the third method that we've talked about is doing completing the square. A fourth way that we don't talk about because it's typically not accurate enough is by graphing. You could graph that, y equals 2x squared plus 12x minus 46, and then use the graphing technique. You'd have to have typically either a very, very accurately drawn graph, or you'd have to use some type of technology to solve it. But we're going to stick to the algebraic methods because they'll actually get you the full answer. So take a moment, do one of them, and then we'll come together and quickly run through all 3 methods as a quick review for solving for a quadratic. So pick one of those methods and go from there. Since I've already done one with quadratic formula, I'll do this first one with completing the square method. Completing the square method starts with having all my variables on the left and the numbers on the right. So I just added 46 to both sides to move that over. It's easiest to do completing the square. Well, it has to be actually. It has to be done so that the first coefficient is a 1. So I need this to be just 1a squared. So in order to get this to be a 1a squared, I need to divide everything by 2. And when I do that, I will get a squared. Let me go back to this color. A squared plus 6a equals 23. And I intentionally left this space open. The completing the square thought bubble is I'm going to take half of the b term and square it. And I'm going to put that on both sides of the equation. So here my b term is 6. So I'm going to take half of 6 and square it, add it to that side. On the right-hand side, I'm going to take half of 6, half times 6, and square it. And when I do that, so half of 6 is 3, and 3 squared is 9. So on the right side, I will have, instead of 23, I'll have 23 plus 9, which is 32. On the left, I'm just going to leave it like this for a second. And the reason why is to see what completing the square is actually doing. This number in here is 3. And 3 squared is 9, which we can think in our head, say, okay, that's 9. But what I'm really looking at is I'm looking for 2 numbers that multiply to 9 that add to 6. And if I did this right, it's whatever this number is. Whatever number is inside the parentheses is the number that will multiply to the last term and add to the middle term. So when factoring, two numbers that multiply to positive 9 that add to positive 6 are a plus 3 and a plus 3. And it's called completing the square because this is referred to as a perfect square. A square, to find the area of a square, it's side times side because the sides are the same length. This is a square because it's same length times same length. So if I were to graph it or make a geometric model of this, it would be a square where one side is a plus 3, the other side is a plus 3. Anything times itself is squared. Then I look and start figuring out, how do I solve for a? In order to solve for a, I need to eliminate the square. The inverse of squaring is square rooting. And this is where the plus or minus comes in, which is one of those little things that you either put on your note card, that when you square root something squared, it's always plus or minus. How do we know that? 3 times 3 is 9, negative 3 times negative 3 is 9. So 9 is a perfect square. If I square root it, it could be 3, it could be negative 3. So that's why it's plus or minus. And then lastly, to solve for a, I subtract 3 from both sides. So a equals 3 plus or minus the square root of 32. This will get you full credit.
So that's the answer?
That would be the answer.
Okay, so don't put that in my calculator or anything?
Don't have to, no, do not put it in your calculator. Do not give that to me as a decimal, leave it as this. So that gets you full credit. For those of you that remember what it means to simplify a radical or simplified radical form, this goes back to two numbers that multiply to 32, one of which that you know the square root of. So the numbers you know the square roots of, besides 1, that becomes a redundancy. You know the square root of 4, you know the square root of 9, you know the square root of 16. You know the square root of 25, 36, 49, 64, right? 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. Do any of those numbers go into 32? 16 times 2? Is that 32? $16 doubled is 32. I know the square root of 16 is 4. 2 is prime. So I could rewrite this answer as a equals 3 plus or minus 4 square root of 2. And there's two answers there, right? It's 3 plus 4 times the square root of 2. And 3 minus 4 times the square root of 2. If this were to be something that was graphed on a, it's going to be a parabola, and it's going to cross the x-axis at 2 different points. Let's see, 4 times that, so that's going to be negative. It's going to look something like this. Those were the 2 points, and this is why the graphing method would not be very good, because it's going to give you decimal approximations to that. And I just want the actual full-on answer. All right. So that's the completing the square method. If you do it the other methods, you will get to the same place. And here's the thing. Because it's like this, I know that I'm not going to actually be able to do factoring. If I tried to use the factoring method, you're going to be trying to come up and know what square root values are, and that's going to be really hard to do. So instead, we're going to do the quadratic formula one more time just so we get practice using it. So 2a squared plus 12a minus 46. Was it minus 40? Right there. 3.
Is a quadratic way easier?
2a squared plus 12a Yeah, minus 46 equals 0. The quadratic formula can be, some people find it easier because they're like, I can just have that formula. I'm going to use it every time and go through it. The hard part is, in a case like this, you have larger numbers.
What was the one you just did? What?
So the A is 2, the B is 12, and the C is negative 46. The method that we just did was called completing the square. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Even though you might have that memorized, I also recommend, especially on exams, write the equation down before you put the numbers in. Because in the haste of taking an exam, too many times I've seen people to forget this negative, or they write this as plus, or they forget the a. But then they carry out the whole process the right way. They just wrote the equation down wrong. Again, that's not, for me, cause for not getting full credit. A formula is a formula. Your ability to memorize used to be like, way back when I started teaching, well, it's not like you're going to have a computer with you all the time. Well, yeah, you do. Or middle school. Oh, you're not going to have a calculator with you all the time. Well, you kind of do. Now, is it more efficient to be able to do some stuff in your head? Absolutely. But that doesn't mean you're restricted to that. So that's why I say write the equation down. Take some time and effort. X equals negative 12 plus or minus the square root of 144. Mistake I see here. If b is negative, people will accidentally make that a negative. Because this is the downside of having a calculator. If you type in negative 12 squared, it'll usually tell you negative 144, even though that's wrong, because your calculator isn't as smart. Minus 4 times 2 times negative 46. All over 2 times 2. So this will be negative 12 plus or minus square root of 144 plus, let's see, 8 times 46.
Is that 2A or ZA?
That's 2a.
Okay.
2. That's why I always cross my z's, because that looks like it could be a z, but it's actually a 2. Got me off track. Did someone multiply 4 times 2 times 46?
368.
368?
Yeah.
All over 4. So x equals negative 12 plus or minus the square, and 144, and it's plus there. Negative times a negative. That's why it's plus. Square root of, is that right? 422? No, that's not right.
512.
Thank you. Way better. 4. And you might be wondering, how does that become the answer we had on the previous slide? This is where 512, I'll use a different color. We'll use white. Blue on black just never goes very well. Square root of 512. Is there a number that goes into 512 that I know the square root of? And if when in doubt, you can always start with like numbers, low numbers like 4. Does 4 go into 512?
Yeah.
Yes. How many times?
A lot.
Tell me.
1, a lot.
It goes in there 1, 11, 12, 8, 9, 10, 11, 32, 8. 128. This is 2. That's why I picked it. But then I'm going to keep going here. Does 4 go into 128? Yes. 32 times. Four is 2. Square root of 4 is 2. And then I go 32. Wait, we just did that one. 16 and 2. Square root of 16 is 4. That is prime. So 512 is equal to 2 times 2 times 4 times root 2. 2 times 2 times 4 times the square root of 2. 2 times 2 is 4. 4 times 4 is 16. This is 16 square root of 2. So back here I'll have x equals negative 12 plus or minus 16 square root of 2 all over 4. Can 12 be reduced by 4 and 16 be reduced by 4? Yes. Negative 12 divided by 4 is negative 3, plus or minus. 16 divided by 4 is 4. And they're multiplied, that's why I can reduce. What's inside the square root cannot be changed. X equals negative 3 plus or minus 4 root 2, which is what we had on the previous slide. And we can't do factoring. This would be similar to the one that we set up, that we'll set up right now for you to use as practice, but similar to the one we did with the airplanes just a moment ago. One hose can fill a tank in 45 minutes. 2 hoses can fill the same tank in 20 minutes. Not seconds, minutes. Find out how long it takes the second hose alone to fill the tank. How would you go about setting that problem up? Finish this one. If you can, take a moment and do it. We will start class on Thursday with that, with this. Remember to be looking at the modules for the check your understanding problems for 6.5 and 6.6.
And you said
We're going to do synthetic division here quick. As a review. Synthetic division is also, like when we're going to divide, you can do either the regular long division or synthetic division. Synthetic division typically is quicker, and many people typically like it more than the long division. One, it's quicker, it doesn't use as much paper space, but also it uses adding instead of subtracting. So for synthetic division, we start with the coefficients. The highest power is x cubed, so it's 4. The next highest power is x squared. The next highest power is x, and there's a value there. And then the next highest power, there's no x's in, is a 12. And the most common mistake is, if one of these is missing, if it went from 4x cubed down to x, you'd have to make sure that you had a 0 in for the x squared. In this case, all of them are here, which is great. And then, when doing synthetic division, the number that goes here is whatever makes this 0. So the answer, so it's the 0 of the function. What makes this 0? If I put x, if I put in 3 for that, I'd have 3 minus 3, that's 0. That's what I put in here. And that's why it's addition, not subtraction. First step is we bring that first term down and then go 3 times 4. 3 times 4 is 12. Gets written there. And then in this case, I'm adding. Negative 12 plus 12 is 0. 3 times 4 is, 3 times 0. 3 times 0 is 0. We add down. Negative 1 plus 0 is negative 1. 3 times negative 1 is negative 3. Add down 9. This is my remainder. Which means this is not a root. If this divides out equally and I get 0 as a remainder, this is my root. This equation then, for when I divide this by that, I'm left with an equation that will be 4x squared. Its highest power is 1 less than the previous. The reason why is I had an x cubed and I'm dividing by an x, so now I'll have an x squared left. Plus 0x, which I normally don't write, minus 1. Plus my remainder, 9 over x minus 3. Now, fun fact, not in the scope and sequence of this course, Well, not within the textbook that we use. And it doesn't really ever present itself as a useful tool except in like math competitions, which I know you guys are probably doing in your free time. If we called that equation up there f of x, and I said, what is f of 3? If I just put x in for 3, and you could put it in there and square it and do all this stuff, but it's equal to the remainder, which is useful when you have really large numbers. But again, that's usually only good for math competitions when people remember that little side nugget of information. This, however, is what we find useful. So we're not going to have time to go back